So how do I calculate density of a rock? Now, obviously, this isn't going to help me for individual minerals, but when I do this, I can gauge relative percentages and see if I can rule out some heavier or lighter minerals that I think it might be. So I can only do density on the whole thing. What do? Well, that's my symbol I use for density. That's the sample, because that's the date I purchased it. I'm going to get an initial mass. I'm going to use my scale. Of course, it's in grams. Tear it out just to be sure. So it has a mass 154.6 grams. So now what I'm going to do is I'm going to take I'll call it volume initial, which will be an amount of water that I put in here to make sure this gets totally covered. I've done this before. So this will go in, the water will get poured first, a known volume. Then this gets put in. So say I'm not going to show you this because I need two hands to do this. Say I put in 200 milliliters. That should totally cover this. 200 milliliters of water. I put that in. The water will rise. Say it's 250, right? So I would take the difference, 250 minus 200, 50. Okay, and density is mass divided by volume. So I'll have a volume initial, which is the initial I put in, that 200 in that case. Then I'll have a V1, which in that case would have been the 250 if it knocked it up. And then I'll get a delta V, which is the change in volume, which would be 50 milliliters. This is the beauty of the metric system. 1 milliliter, STP, is equivalent to 1 cubic centimeter. Because we do density, we do mass, we'll do mass in grams, and we'll do volume, so the unit will be grams per centimeter cubed. 1 cubic centimeter is equal to 1 milliliter. You don't get that in the imperial system, so I can do this in milliliters and just swap the units. So that's the process I'm going to do, and I'll show it to you when it's complete. What I'm going to do to fill this beaker with my initial volume is I'm going to use this graduated cylinder because it's more accurate than this one is, and I have 100 milliliters in there right now. So we'll put that in. That will not be enough. You can see this beaker is pretty close, all right? But that's not going to be enough, so I'm going to put in at least another 100. Well, actually, maybe 50 will do. Actually, the less water you use, the more accurate this is. It sounds weird, but it's true. So at least that's from experience. And the smaller the specimen, the smaller the sample, the more accurate this is, because stuff like this is really inaccurate. So I'm going to put another 50 or 100 in there. Okay, I won't need this. Put it away. I decided to just do another 75 milliliters, and you can see that's pretty close. I have 175 milliliters as my initial volume. Now, I'm just going to, best I can with as little splash as possible, set this in here. I have to make sure it is entirely engulfed in water. All right, and it is. So now what do? Well, that's going to be my V1. And just by looking at this, we went from 175 milliliters to somewhere between 225 and 250. But I'm going to get a better, more accurate number than that. I drew a line here with a erasable marker. I'm going to take this out because I'm done with my rock, and it doesn't matter if I get my hand covered with water or not. Put it over here, dry out. Now I'm going to fill this as accurately and precisely as I can to that line. When you do this, you want to be consistent with how you fill it up. So if you drew your line when the rock was in there at the top of the meniscus instead of the bottom, you want to do that again just to be consistent. So I got it as good as I could. Now what I'm going to do, like I said, it looks like it's probably about 240-ish milliliters. But to get it as accurate as I can, I'm going to dump it in here. Now, obviously, I'll have to dump it a couple times. I have many of these. I also have ones with blue gradation on them. And I just have plastic ones because I just use this for density, and generally it's warm enough in here where I don't need to worry about it. One thing I forgot to mention, when you're doing the density test, after you've put your water in, you put your rock in, the water comes up, you draw your line, all right? You take the rock out without moving this as much as you can, because this is really actually pretty level, but it is not perfectly level. So if I start moving it around, my line's going to be off. It's going to decrease my accuracy. Okay, so this is 100 milliliters. I've already filled and dumped it twice, so that's 200 milliliters, and this is what was left. Now, although as long as I'm consistent filling it to here after I draw the line, if I draw the line on top of the meniscus, because this is a wide beaker, the top of the meniscus and the bottom of the meniscus aren't going to be any significant thickness. But when you read it on something like this, it's narrower, you want it to be from the bottom of the meniscus, and I hope this picks it up. But we look like we have about 234 3/4 or we'll just say 235 milliliters. We're really close to that. So my V1 is 235 milliliters. My initial is 175, and this pencil keeps, so it's I'm going to do 235 milliliters minus 175 milliliters. That gives me 60 milliliters. 60 milliliters is my change, my delta V. 60 milliliters. Okay, so now I'm simply going to take 154.6 grams divided by 60 centimeters cubed, because remember 1 milliliter is equal to 1 cubic centimeter. So I can just swap the units. Well, how does this rock compare with other densities? Rock is not a granite. It has voids in it, so it's on the bottom part of the QAPF diagram. But I have a chart here of basic rock types. Now, no void rocks are on here. Well, there are some, but not ones that, no nepheline void cyanites on here. So the closest thing on here that we can see is actually granite, all right? So granite is the closest rock here now to what we have there. So the densities, now this is in kilograms per cubic meter. So that's why it's 2,330. So to convert to grams per cubic centimeter, we just moved the decimal 3 places and now make it 2.330 grams per centimeter cubed. So that's another thing with the metric system. It usually just involves moving decimals. So this is a lower limit. That's a lower density. This is the higher, or this lower density. This is the higher density. This is typical density, 2.64 grams per cubic centimeter, and this was 2.58. So it is a little, it's below the average, but it's not that far below, and it's well within. So this you could describe this rock as being granitic, but it is not a granite. So that's another thing you got to watch for with geologic terms. A lot of terms that are used for one thing are also used for another. If you call this a granite, it better be a granite. But if you use the descriptive term granitic, it can be a whole host of things. It's just one of those things. All right, that's the chart I use. So what will this help me do? Well, I'm pretty confident that number. Like I said, it's a little low. I actually expected it to be more like 2.7. But the 2.58 makes sense because you look at this, even though there's a lot of black mineral in it, mafic, which would be the heaviest, it doesn't make up too much of the rock, right? Maybe 10%. I'll actually get a decent percentage later. But so we've begun our testing on what I suspect is a nepheline void cyanide. We do know it has voids in it. It has sodalite, the long wave UV, it glue bright orange, but did not glow in shortwave. We ruled out lorenzonite tentatively because it did not fluoresce. The rock did not fluoresce at all, let alone yellow to dull green under shortwave UV. So that's it for now. I'm going to go inside and I will continue tests later. But I just wanted to get the basic density one done now. And hopefully you'll find this as exciting as I do. Well, exciting as you can, I guess. But anyway, that's it. If you have any questions or comments, leave below. And I hope you learned something.